Welcome back to ECE 442-542. I have a couple of things that I'm wanting from you before you leave today. One of those is on the bottom of the screen, but homework number 2 to start is due on Friday. And you might want to look at that because I'm getting some questions already about some of the problems, and I've tried to explain something in words, and it may not be that clear, meaning you might need a little bit of time to digest what it is that's being asked on some of those questions. Exam number 1 is a week from Wednesday, and it will be covering material on homeworks 1 and 2. And if we get far enough today, maybe today's material will be where we stop for exam 1, but I'm guessing we may have to go into Wednesday a little bit for material. Now, to get you thinking about exam number 1 and to relate this to what you had to do on your passport as far as learning, how do you learn and what's an effective way to do some of this learning, one of the concepts was retrieving information or ideas or solution techniques that you've seen or worked on in the past. Let's see if you can match the list of topics for exam number 1 that's now posted on D2L. Before you've looked at that list, try to recall what we've done in class and on homework and see if you can come up with the ideas, the concepts, the strategies that we've worked on so far in this semester prior to maybe looking at what's on D2L. Just as a way of retrieving that information from here because, well, I guess you can't see that if you're listening to this, but I was pointing to my head. I thought maybe you could hear the empty space when I was clicking my stylus. Oh, that's not a hand. That's just you're adjusting your headset. Okay, I kind of have to adjust my headset. Where was I? Retrieval practice, but a review exam. And I forgot to check whether these dates and times are even acceptable. But if you could vote and give me that vote before you leave tonight, maybe we can start to converge on a time. If you want to have it physically, I could simply get in a closet and record what you've come up with, and what you will come up with are topics and questions that you would like to see addressed in that exam number 1 review. Those are the 2 things that I need from you: a question or topic, or topics, or questions, and when would you, or what type of a review would you like to have? Would you like to just listen to it at your leisure, or would you like to attend? I'm going to try to record it even if we do have it live, so if you can't make that particular time, but I would like to see what you are thinking in terms of a review session. Would you like to have one in person or a recorded version? For today, this is where I would like to get to for exam number 1, topics. Let's review the unit step waveform, how we might find the Laplace transform of that in the continuous or analog setting. What does the pole zero diagram look like? Let's do the same thing in the digital domain. Then let's follow through and look at the exponential waveform. You should be very comfortable with that in the analog setting. We just started looking at deriving that for the discrete time or digital case. We'll finish that up, and then we will look at the Z-transform of an exponentially damped cosine. On homework 2, you'll have to rederive that for an exponentially damped sine. But that now gives us pretty much all of the waveforms that we might be interested in dealing with, or most of the waveforms we'll be dealing with in this class. Constants, that's the step. Exponentials, those are real poles that we may have to deal with. They could be stable or unstable. And then we have these damped sine and cosine, exponentially damped sine and cosine waveforms, and it'd be nice to know what do those look like in terms of pole zero patterns in the z-plane. I'm hoping that you know what those look like in the analog case or for continuous time. Then we'll really just state some Z-transform properties that are consistent with Laplace transform properties, which allows you to maybe obtain the Z-transform of more involved waveforms or signals. And we will try to look at the frequency response of a system. H of Z could be a plant, some mechanical system, an electrical system. It could be a filter. But now we excite that. We put as an input some sinusoid. And what does the output look like after it gets filtered or processed by that H of Z? Do you remember how you did that for the Laplace case? What did you do if this was H of S and you excited that system with a sinusoid or a cosine? That's where we want to head for the discrete time. And one way that you can maybe start to think about this is, where did you get sinusoidal signals, or where were sinusoidal signals located in the S-plane? If you said, where are the poles associated with this waveform in the complex S-plane, and it's a sinusoid or a cosine, a sine or a cosine, I'll just maybe say a sinusoid, where would those poles be located? Do you remember? If you Laplace transformed a cosine, where would the poles of that transformed waveform be in the S domain? Pardon? Off of the real axis. Now I want a pure sine wave on the imaginary axis. That's where they are in the S-plane. You'd have poles that are positive and negative of each other. You've got the twins, one's positive and one's negative, and those two then give you a cosine or a sine, and their distance away from the origin, their vertical distance, represents their frequency of oscillation. Now, where does the imaginary axis in the S-plane map to in the Z-plane? What's another way of thinking about that imaginary axis? As another hint, does that give you some kind of boundary, the imaginary axis? If you're on the left of that imaginary axis, what do you know about your signals? They're decaying, aren't they? If you're to the right, in the right half plane of that imaginary axis, they're expanding or growing. That imaginary axis is our boundary for stability. Now, with that clue, where do you think we will be associating sinusoids, not damped sinusoids, but pure sines and cosines in the complex Z-plane? On the unit circle. The imaginary axis in the S-plane now maps onto the unit circle of the Z-plane. And you can see that. If you now say S is equal to j omega, now Z is equal to e to the st, now you have e to the j omega t. That's something that has a magnitude of 1 and some angle. That's right on the unit circle. Maybe you need to be sketching this. I'm just sort of talking, but start thinking about that, and that's where we're headed at the end of today's lecture, is the idea. Let's review by getting warmed up. So before you do any kind of physical exercise, you usually kind of loosen up, right? Did everybody loosen up yesterday before watching something? I don't know. Hopefully they loosened up. Now we need to loosen up our muscle up in our head to get going for the next things, which eventually will be the exponentially damped sines and cosines. The unit step in the analog case looks like this blue line. In the time domain, I have the time domain on the left and the frequency domain on the right. What's the Laplace transform of a unit step? This is a fill in the blank. And it shouldn't be that, I hope, it's not that challenging. What's capital U of S if little u of t is the unit step? This is just 1 over S. Now, where do we plot? This is now an S-plane plot. It's a little bit wide maybe, but we now have that S-plane, complex S-plane, the real part and the imaginary part. Where do we find the poles and zeros associated with this unit step? Right at the origin, right? And there's only a pole, and that's then this x. Well, that's supposed to be on the origin. So you can put yours a little bit more accurately on the origin. What about the digital case? Here is our time domain unit step. It has a value of 1 at each time instant. 0, 1 to all non-negative time is this value of 1. Do you remember what we derived for capital U of z, the Z-transform of that unit step? And now I'm wanting you to recall that, retrieve that without looking back in your notes. Or if you can't remember what that was, do you remember how we derived it? How did we derive that result? What did we plug in for little u of n? That's the Z-transform definition of a one-sided Z-transform. Capital U of z is this sum from n equals 0 to infinity, little u of n, z to the minus n. We're weighting each of these instances of u at various points in time, which are determined by n, by this complex exponential, z to the minus n. What's little u of n? That's always 1 for a unit step, isn't it? Now we are summing z to the 0, z to the minus 1, z to the minus 2, z to the minus 3. What's the common factor between each of those subsequent terms in that sum? What's this geometric scaling amount when we go from z to the 0 to z to the minus 1 to z to the minus 2? How do those all differ? What's the factor? What's the scaling factor? Z to the minus 1. And that's what we had to multiply by in order to sort of compare or subtract these different expansions for capital U of z. Then we divide by the result, and we ended up with 1 over 1 minus z to the minus 1. Is this making sense? It should. And if it doesn't, then we need to work a little bit at that. And then you could rewrite this. That's now in terms of z to the minus 1s, but you could rewrite that in terms of z's by multiplying that by 1, where 1 is now z divided by z. Or you could factor out the z to the minus 1, and then it will kick upstairs, however you like to think about it. In terms of powers of z, or polynomials in z, the unit step has a Z-transform of z over z minus 1. Now, where are the poles and zeros of that? Again, it's not that hard. We have a 0 right there at the origin. and we have a pole at 1. And that pole at 1 is consistent with our pole in the S-plane, which was at the origin. Now, if you're very used to thinking about the origin in the S-plane, now that maps into this point z equal 1 in the z-plane. There is our pole and zero diagram for the unit step. What about this exponential waveform? E to the AT. We talked about this at the very end of last lecture, but depending on what A is, whether it's positive or negative, influences the shape of that exponential in the analog case. If A is negative, then we have this exponential decay, e to the minus 6t, or e to the minus t, e to the minus 3t. Those now have this exponential decay, and the speed of that exponential decay is influenced by the magnitude of that A. If A is positive, then we have the red curve, and we have an exponential increase or growth curve, e to the 4t. That's growing unbounded exponentially. What's the Laplace transform of e to the AT? And now let's just keep A as positive for illustration purposes. If you had the Laplace transform e to the AT, what would that look like as capital X of S? Do you remember? And if you don't, then you need to go back and either rederive it or convince yourself of what that is. Or maybe you're more familiar with Laplace transforming e to the minus 2t. What would that look like in capital X of S? Talk to your neighbor. Convince your neighbor that you're correct. What is the Laplace transform? And now this will teach you to sit way away from a neighbor, huh? Now, some of us engineers kind of like to be alone, right? We kind of like to have some space. Don't even have to be an engineer to like some space. Some of us like to be close. That's fine. But what's the Laplace transform of e to the AT? One over S minus A is what I thought I heard. Does that seem consistent with what you were thinking? Thumbs up if you think it was. Thumbs down if you disagree. If you're not quite sure, it could be sideways. 1, 2, 3. I even don't see some thumbs. So this is actually correct if A is positive. It's in the red, which is consistent with that red curve. This now gives us one pole, a real pole, on the positive side of the S-plane. Here is now an A, which is positive, which would correspond to this growing exponential, this exponential rise. We're used to liking or seeing e to the minus something, and then that pole ends up in the left half plane, which is the good place, where it's stable. But depending on what A is, whether it's positive or negative, that influences what side of the imaginary axis that is on. But you need to get comfortable with this, because now we're going the next step, which is to examine the digital version of this, which could be a sampled version of this waveform where we would replace little t with little n capital T. That's sampling this waveform. Or it might just be a generic exponential waveform. Maybe it's just given by R. And R could be, in magnitude terms, less than 1. Then we'll have this exponential decay. R could be bigger than 1. Then we will have this exponential growth. And we want to now figure out what we actually have. Now, before I should have moved on, where is the, oh no, let me, should I go back this far? No, let's just move on. I was going to say, where's the region of convergence for that unit step, but we'll pick that up in a minute. Let's now figure out what we have relative to the Z-transform of this exponential. We are now looking at capital X sub c of z, which if you were looking for partial credit, you would say, oh, I'm just going to write down the definition of the Z-transform. That's this sum from n equals 0 to infinity of the time domain waveform weighted by this complex exponential. Little x sub c of n weighted by z to the minus n. And now you can simply use that as a guide or an algorithm. That sum, you can simply start writing down what that translates into explicitly. You could plug in all these different values of little n. You could say, oh, I have x sub c of 0 times z to the 0. That's just 1. Let me just leave that one off. Plus x sub c of 1, z to the minus 1, plus x sub c of 2, z to the minus 2, etc. But we actually know what x sub c of n was. That was this r to the n. That's how we defined it. If we substitute or replace that structure for little x sub c, then we start to maybe see this making a little bit more, being a little bit more clear. Little x sub c of 0, that's r to the 0, that's 1, plus r z to the minus 1, plus r squared z to the minus 2, plus r cubed z to the minus 3, and that pattern continues. And if we are thinking back to the way we found this closed form expression for the unit step, we were trying to identify a common scaling factor or term that was multiplying each of those subsequent values in that sum. How do each of those expressions differ from one another? Or how can we rewrite this? We could say, well, that's 1 plus, let's say, z to the minus 1 plus rz to the minus 1 squared plus rz to the minus 1 cubed. And hopefully that now starts to look like something that we can manipulate. We've identified this similar factor, r z to the minus 1, which allows us now to say, okay, I know that capital X sub c of z is this 1 plus rz to the minus 1 plus rz to the minus 1 squared. When will that infinite sum be well behaved, or when will it converge? This blue right-hand side converges when what is true? If you thought of this as 1 plus x squared plus x cubed plus x to the fourth, what would you need property-wise to know that that's going to be a converging sequence? What do you know about x? X needs to be less than 1, doesn't it? And x, we said, is this entire piece, rz to the minus 1. We're now saying that this converges when r z to the minus 1 is less than 1, or the magnitude of that product, r and z to the minus 1, is less than 1. We were defining that as x. And we convinced ourselves maybe before, in earlier lectures, that if we have an x, then as long as that x is less than 1 in magnitude, that sum is going to converge. Let's now assume that we have this capital X sub c of z converging. We're now assuming that r z to the minus 1 is less than 1. If that's the case, we can scale that first line by that same common factor, rz to the minus 1, and now I have rz to the minus 1 plus rz to the minus 1 squared plus rz to the minus 1 cubed, etc. And if I subtract the bottom from the top, I now have 1 minus rz to the minus 1, capital X sub c of z. Most of the tail goes away, and we're left with just 1. And now we have a closed form expression for capital X sub c of z for an exponential discrete time waveform. This now says that if we solve for capital X sub c of z, we now have 1 over 1 minus r z to the minus 1. And if you don't like the way that that makes you feel, having a z to the minus 1 variable, we can convert that by multiplying top and bottom by z, or the whole thing by 1, and we now have z over z minus r. And that converges. That's true. That Z transform exists as long as rz to the minus 1 is less than 1. But we can rewrite that as r over z magnitude less than 1 Now the magnitude of that quotient is the same as the quotient of the magnitudes, and we can push that magnitude of z to the right-hand side, and now we see that r needs to have a magnitude less than z in order for that z transform to exist. So this z transform of an exponential is given by z over z minus r, and that converges as long as this complex number z is bigger than r. And can we visualize that in the complex plane as a pole zero diagram? Here is our z-plane, the real part of z and the imaginary part of z. Where are the poles and zeros of that z transform? We have a 0 right at the origin, and the origin in the z-plane is not the same as the origin in the s-plane, right? And where is your pole located? It's when the denominator is equal to 0, isn't it? So we set that denominator equal to 0. That will give us a pole. That says that z is equal to capital R. If capital R is 6, then z is equal to 6. We have a pole at 6. If capital R was minus 3, then z would be, the pole would be at minus 3. If capital R was 1/2, then the pole would be at 1/2. Let me just draw a pole there at R. And relative to that pole zero diagram, where is the region of convergence of that transform? What values of z, if we plug them into that formula, would allow that z transform infinite sum to be to exist or be valid? We need z, all values of z, to have a magnitude bigger than r. So we use that r as a radius. If you had a compass, which I don't have, you would now, so bear with me, this is supposed to be a radius of circle, or of radius capital R, and the region of convergence is every point in the complex z-plane outside of that disk of radius capital R. Here is the ROC. That's for those that are texting this. You don't have to type in or text region of convergence. You just say ROC, the ROC, the region of convergence. And what we're going to find is that where is the unit circle relative to that region of convergence? If the region of convergence contains the unit circle, then we have a stable pole or exponential waveform. Meaning if little r is 1/2, then the unit circle is outside that capital R, and that unit circle is contained inside the region of convergence. If capital R is 2, where's the unit circle relative to that picture? It's now inside the region of convergence. The unit circle is not contained in the region of convergence, and that system, that waveform, is unstable. We'll go into that a little bit more, but that's now something that we can think about. Now that we've done that, can we go back? I can sort of cheat because I can quickly slide back and forth. Can we now determine the region of convergence for this unit step? Could we sketch the region of convergence for this pole zero diagram? What did we derive for this? I guess we derived it last time. What did we know we had to have? Z minus 1 less than 1, didn't we? Which means Z as a complex number needed to be bigger than 1, its magnitude. The region of convergence now is every point of Z that's outside the unit circle. If we sketch the region of convergence here, here's minus 1, here's J, here's minus J. Here is our region of convergence. And that's what we need to start feeling comfortable with or getting comfortable with. These region of convergences relative to our poles and zeros. Questions on that? This is now the Ztransform of an exponential waveform in the digital case. Little x of n is r to the n. That's the time domain, and this is what it looks like or has for its Ztransform. Yes?
So you're saying so does the region of convergence have to be within the bounds of the to be for it to converge?
So now we want to maybe try to rephrase the question. We want the unit circle to lie inside or within the region of convergence. So the unit circle needs to be contained, or in this case, larger than whatever that capital R is. If capital R was 3/4, we're good. If capital R is 0.99, we're good, barely. I wouldn't like that. If capital R is 1, what are we? What's this waveform in the time domain if capital R is 1? Now we have 1, 1, 1, 1. What do we have in the time domain? A unit step. And if that was really a system that had this pole zero diagram where capital R is 1, I could excite that with a constant and it would start giving me an unbounded waveform with time. So it's not, people might refer to that when they have poles on the unit circle as marginally stable. I would say let's not even think about that. Let's just kind of say that's not really what we want. Okay? It's not going to, because we could apply a bounded input and obtain an unbounded output. So that would be that would not be a bounded input, bounded output stable system. But now we're just looking at signals and just signals or waveforms, and we're not really talking about the combination of systems and signals. Let's look at another waveform or a signal. What about exponentially damped sinusoids? Learning is always usually enhanced if we can relate what we're trying to learn in the new setting with something that we hopefully already know. And now I'm hoping that we already have some familiarity with this continuous time exponentially damped sinusoid. Suppose I say, let's look at x of t equaling e to the minus sigma t cosine omega sub dt t greater than or equal to 0. I'm going to run out of space, so now instead of going left to right, I may go up and down. But what's the Laplace transform of little x of t? Here, let's just assume sigma is some positive number, so we do have damping. We have e to the minus 2t. It's oscillating at some damped frequency, omega sub d. That might be 3. We now have e to the minus 2t cosine of 3t. What does that look like as far as its Laplace transform? Do you remember? And if you don't, then you need to get comfortable with that Laplace transform. Does anybody remember? Maybe the numerator, maybe you kind of go, I can't remember exactly what the numerator looks like, but I hope you remember what the denominator looks like. Where are the poles of this exponentially damped cosine in the S-plane? Do you remember? And for those of you that had me in 441, I may call on you, shake you if you don't remember this, because I'm really giving you a big hint with sigma and omega sub d relative to where we were plotting those in the S-plane. So I'm hoping that if you don't see this right now, eventually you'll start to get comfortable with when you see that in the time domain, you immediately start to see poles in the S-plane. You can go, oh, I see where the poles are in the complex S-plane. What does the denominator of this look like? Anybody want to be brave now that I've put you on alert? That's the denominator. Oh, I guess it's not a touchdown, is it? But it's good, right? The denominator is good. Now, with respect to the cosine and the sine, maybe you have forgotten that, but the cosine is this s, and in the sine, it's just the frequency. So the cosine is s plus sigma when we have this shift of e to the minus sigma t, but this is now the Laplace transform of this exponentially damped sine and cosine for this particular case. And we can now sketch in the S-plane the poles and zeros of that expression. Here is j omega sub d. Here's minus j omega sub d. We're over into the left half plane, this distance minus sigma. Our poles are at minus sigma plus and minus j omega sub d. Those are supposed to be complex conjugates of each other. If it's not clear that they're the same distance, they're supposed to be. And we have a 0 right at minus sigma. That's the transform pair, the time domain and frequency domain for an analog waveform, which is an exponentially damped sine and cosine. That's continuous time. What happens in the discrete time? First, maybe it'd be nice if we even sort of had a feel for what that might look like as a sampled waveform. Let's now start with x of t. We now want to write this as complex exponentials, which means we need to go get Euler and wake him up, right? And express this cosine as a combination of complex exponentials. Meaning, let's now rewrite this cosine omega sub dt is e to the j omega sub dt plus e to the minus j omega sub dt all over 2. That's Euler, which now allows us to write this as 1/2, and I'm going to go ahead and distribute that e to the minus sigma t through both terms in the numerator. I've factored out the denominator as a 1/2, and I now have e to the minus sigma t, e to the j omega sub dt, plus e to the minus sigma t, e to the minus j omega sub dt. That's writing that e an awful lot. We know the properties of these exponents. We can simply add exponents when we're multiplying those two terms, which says that we could rewrite this as 1/2 e to the minus sigma plus j omega sub d t plus e to the minus sigma minus j omega sub d t. And I'm going to now just call this little s sub 1. That's a complex number, minus sigma plus j omega sub d. This is also a complex number. It's actually the conjugate, but I'm just going to call them S1 and S2 if I need to. And actually, I'm not going to. I'm just showing you that those are complex numbers by saying S1 and S2. Is that clear? You can have a sigma, let's say it's 2, and omega sub d is 3. Little s sub 1 is minus 2 plus j3. S sub 2 is its conjugate. It's minus 2 minus j3. And those are now 2 points in the complex S point. That's still a continuous time waveform. We can obtain a discrete time waveform by sampling or replacing little t by little n capital T, sampling or dicing up that time axis into multiples, integer multiples of the sample period capital T. What I'm saying is let's now rewrite or sample little x of t by replacing little t by little n capital T. And now we have 1/2 times the quantity e to the minus sigma plus j omega sub d little n capital T plus e to the minus sigma minus j omega sub d little n capital T. Now, we pushed things together before, now let's pull them apart, because we can see that there's a common factor in those two terms of e to the minus sigma little n capital T. In both of those pieces, let's factor that out by separating that sum of exponents into two pieces. We can now write this as 1/2 e to the minus sigma little nt e to the j omega sub d nt plus e to the minus sigma nt e to the minus j omega sub d nt. Make sure I'm not falling asleep up here. Is my algebra okay? Now let me factor out that e to the minus sigma t to the n. I can do that. And I now have, since that product of exponents is one of the pieces raised to that one of the exponent pieces, which is little n, our time index. And now I can say, well, I also can write this as e to the j omega sub dt to the n plus e to the minus j omega sub dt to the n. And if I wanted to, I could collapse this omega sub d, capital T, into a new variable, theta, where now I have e to the j theta sub dn plus e to the minus j theta sub dn. And oh, Euler is just screaming to come out, isn't he? That's e to the jx plus e to the minus jx. That's two cosines of x, which now says that we can write that as 1/2 e to the minus sigma t to the n 2 cosine theta sub dn. And those 2's and divided by 2's, those clean up nicely, so that we now have an expression for an exponentially damped cosine waveform for a discrete time system. We have e to the minus sigma t to the n cosine, and if we wanted to, we could replace theta sub d with omega sub dt to get us back into sigma and omega sub d that we started with. Remember, theta sub d we just defined as omega sub d capital T. We could view that as just some number r, couldn't we? E to the minus sigma t. If sigma was 2 and capital T was some small value, that was our sample period, we have e to the minus something small, maybe that's 1/2. We now have 1/2 to the n. That's now how quickly we're decaying, exponentially decaying. That's our capital R. And how we're bouncing around is this cosine of theta sub d n. Meaning, if I could draw this, we have this decay envelope that's e to the minus sigma t, and we have a cosine omega sub dt, which says now that we have a cosine waveform that's now getting squished, squeezed by this exponential decay. And now in discrete time, we are actually just sampling that at particular instances, depending on what our sample period ends up being. That's now an exponentially damped cosine waveform in discrete time. Those are the blue lines that are in this decaying exponential that's oscillating back and forth depending on the frequency omega sub d. What we want to do is figure out what's the Z-transform of those blue lines. This is just the time domain waveform. But we tried to relate that to something that we were comfortable with to start with. Now let's look at the Z-transform of an exponentially damped cosine. Again, you have to do the twin. You're going to need to do the sine on your homework. Maybe that woke you up. Here's little x of n. We said that that's this 1/2 r to the n, or it could be written as 1/2 r to the n. Then we have an ej theta sub d n plus e to the minus j theta sub d n. That's one way to parameterize this exponentially damped cosine. And that's somewhere up in that derivation, is a way to write it this way. Let's now find the Z-transform of that time domain waveform. We now want capital X of Z, which is now this sum from n equals 0 to infinity, of little x of n, that's 1/2 r to the n, e to the j theta sub d n plus e to the minus j theta sub d n, z to the minus n. This in squiggly braces is little x of n. That's the definition of the Z-transform. Let's break that up into two pieces. The two pieces naturally coming into play because of that plus sign in this expression. Meaning, let's rewrite that expression for capital X of Z as two infinite sums. We have a sum from n equals 0 to infinity of 1/2 capital R to the n, e to the j theta sub d n, z to the minus n, plus 1/2 summation n equals 0 to infinity r to the n, e to the minus j theta sub d n, z to the minus n. And before we get too nervous or anxious, let's pull that n out of the exponent in all of those terms, in each of those sums. Meaning, I can rewrite this as 1/2 sum from n equals 0 to infinity of r e to the j theta sub d z to the minus 1 to the n, plus 1/2 sum n equals 0 to infinity r e to the minus j theta sub d z to the minus 1 n. And let's just do our normal way of thinking. That's too messy looking. Let's just call it some new variable. Let's call that capital R e to the j theta sub d z to the minus 1. Why don't we just call that x1 and this x sub 2? So that now we have simply 1/2 sum x1 to the n equals 0 to infinity, plus 1/2 sum x sub 2 to the n equals 0 to infinity. And that's capital X of z. That's now looking like something we've been doing all along. We know how to find a closed form expression for x to the n when it's the argument in that sum. This is now 1 plus x1 plus x1 squared plus x1 cubed. We know how to rewrite that in a closed form expression. The first one is that, right? x1 is just the geometric factor that changes with each of these terms in our infinite sum. If I give you that answer, I hope you can write down the second one. And now we just have to rely on our algebra teacher. If this is now capital X of z, let's combine those two pieces into one ratio and see what we end up with. Meaning, let's get a common denominator so that now capital X of z looks like that. What's in the numerator because of that first factor in the sum of two pieces? In order to get that first sum back, what do we need to include in the numerator? Will that get us what we have in the first piece of that two-piece sum? We just cancel the x minus, or 1 minus x sub 2. Then we can obtain the second piece likewise. Now, let's do some combining. We have 1/2 plus 1/2 upstairs, which gives us 1. Then we have minus 1/2 x1 plus x sub 2. I'm just combining or rewriting the numerator. Downstairs, I have 1 times 1 minus x1 times 1 minus x2 times 1 plus x1, x2. We didn't start with x's. We started with r's and theta sub d's. But we defined those x's in terms of r's and theta sub d's. Let's now see what those two different terms give us. x1 times x2. in terms of the r's and theta sub d's. We have x1 times x2. x1 was r, e to the j, theta sub d, z to the minus 1. X sub 2 was the same, it was just the conjugate of that middle piece. What's the product return? Do you see what's happening? E to the j theta d times e to the minus j theta d. We add the exponents. We get e to the j 0. That's just 1, isn't it? So that goes away, and we're left with r times r and z to the minus 1 times z to the minus 1, or this reduces to r squared z to the minus 2. That's one of the pieces of our Z-transform. The other pieces will come to us if we find what x1 plus x sub 2 looks like. This is now r, e to the j, theta sub d, z to the minus 1, plus r, e to the minus j, theta sub d, z to the minus 1. We have a couple terms in common. And now you can make your trig teacher happy by recalling Euler again, because that's setting there in parentheses. We can now say that that's 2 cosines, or we now have 2 times r, z to the minus 1 cosine theta sub d. That's x1 plus x2. We have x1, x2. We just need to replace those or use those in this expression for capital X of z, and we'll have our Z-transform of this exponentially damped cosine. We now can say that capital X of z is now 1 minus 1/2 x1, x2, but x1, x2 had a 2 there, so the 2's cancel, and we have 1 minus r z to the minus 1 cosine of theta sub d. Then we had 1 minus x1, x2, and that was just 2r z to the minus 1 cosine theta sub d, plus x1, x2, which was r squared z to the minus 2. And we may not like that in terms of z to the minus 1. We can clear the z to the minus 1's by multiplying by 1, which is z squared over z squared. Or we now have capital X of z is now z times z minus r cosine of theta sub d. And downstairs we have z squared minus 2r cosine theta sub d z plus r squared. That's now the Z-transform of an exponentially damped cosine. What's the exponential damping piece in there? That's corresponding to capital R, isn't it? So if you have a collapsing, then capital R is less than 1. The frequency that that's bouncing back and forth with is given by theta sub d. What's the pole zero diagram of this look like? We now have x of z is z times z minus r cosine of theta sub d, z squared minus 2r cosine theta sub dz plus r squared. Do you see where that might be in the complex z-plane, any of this? Suppose that r is less than 1, and theta sub d is, I don't know, 30 degrees. It's probably in radians, but I think in degrees, so it's just 30 degrees, let's say, theta sub d. Can you put any poles or zeros down? I hope you see there's one zero just screaming at you. You're looking for values of z that cause the numerator to go to 0. You better see one just screaming, right? You do have a 0 right at the origin. That's the z sitting out there factored by itself. Where's the other 0? It's some distance on the real line, isn't it? Positive real line, and it's at some point, let's say r cosine of theta sub d. Maybe I will tell you to prove this to yourself, that the poles are here and here, where this distance, well, that's a pretty bad straight line, but that's a distance r away from the origin, and this is theta sub d, meaning this distance is r cosine of theta sub d. This distance is r sine of theta sub d. So now if somebody gives you an exponentially damped cosine with a damping of r and basically an oscillating piece determined by theta sub d, you now know the pole zero diagram of that in the complex z-plane. And you should be able to, you can go home tonight and find the roots of that denominator using what? MATLAB. What are you going to do for r and theta sub d unless you have the symbolic toolbox in MATLAB? You'd have to find specific values for r and theta sub d. I'm claiming that you can do this for variables theta and r sub d. Use the quadratic formula. It's a quadratic, right? Factor that or find the roots using the quadratic formula and see if the poles aren't at a real part of r cosine of theta sub d and an imaginary part of r sine of theta sub d. And the 0 has the length r cosine of theta sub d. Convince yourself of that. You need to derive the sine. We obviously have a couple more points to cover before we finish our exam 1 material, but I need questions or times that you would like, or not a time, just a recording of the review session. If you've thought about that, if not, maybe I'll put a Dropbox or something on D2L and you can type in or write down your question somehow that way. But I need to start collecting these so that I have a clue as to what's not clear, what is clear relative to the material we're covering. So I will see you in a couple of days on Wednesday, and we'll pick up somewhere from here with Z transform properties.